In this video, we're analyzing the localized molecular orbitals involved in the Baeyer-Villiger reaction, especially their effect on the migration and effects on stereochemistry. In this reaction, MCPBA is the oxidant that forms the tetrahedral intermediate after the first two steps of the reaction, acid-base, then the reaction between the nucleophile and electrophile. As we saw in the preceding video, the secondary group migrates preferentially over the methyl group. For that group to migrate, the sigma migrating bond has to be antiperiplanar to the breaking OO bond. The sigma bond is a filled bonding molecular orbital with 2 electrons in it. It is the highest energy occupied molecular orbital, or HOMO. To form a new bond, the HOMO must overlap with an empty orbital. The lowest energy unoccupied molecular orbital is the OO sigma star bond, the empty antibonding molecular orbital. In the transition state of this reaction step, the HOMO and LUMO overlap to form a new sigma bond. A new sigma star bond also forms. As the new sigma bond forms, the OO sigma bond breaks, with the far oxygen atom taking the electrons. Notice that this is similar to the overlap that occurred in the SN2 and E2 reactions. To summarize, when the tetrahedral intermediate collapses, a non-bonding electron pair on the hydroxyl oxygen comes down, forming a new pi bond. This CC bond breaks and migrates with the secondary substituent to form a new CO bond, and the OO bond breaks, with the far oxygen atom taking the electrons. Because the electrons from the nucleophile, HOMO, are staying in the same relative position compared to the other substituents on that migrating carbon atom, the configuration of the migrating group does not change. In other words, this reaction proceeds with retention of configuration at the reacting carbon.